Here we're going to apply some implicit differentiation to some real-life problems, and it's called related rates. The first thing we're going to do is talk about expanding or shrinking a square. So we have the sides of a square increase at a rate of 3 meters per second. So the sides are getting bigger and bigger by 3 meters per second. That must be a derivative that we're given, right? That's a rate of change. So that's going to be a derivative instead of just a constant, like variable in the problem. It says, at what rate is the area going to be changing? Right, if you make the sides of a square bigger, what's going to happen to the area? Is it going to stay the same? No, the area is going to also get bigger as well. So we're going to find a derivative there. How fast is the rate of the area changing when we know the rate that the sides are changing? And the sides are starting out at 10 meters long. So in these problems, we are always given a rate and solving for a rate. That means I'm going to be given how I know one thing is changing, and I want to see how it is affecting the other. So like with the weather, if the sun is getting hotter, the sun is rising and the sun is coming out, that's going to change how the overall temperature is. So if you change one thing, it normally changes the other. Same thing with buying stuff. If you see that there's a huge sale at your favorite store or something, you're more likely to buy stuff because as prices go down, demand goes up, versus if like gas prices are getting very expensive, there's going to be less demand. You're going to ride it out on E for as long as you can. So there's a lot of things where if you change one thing, it affects another rate. So here we're changing the side of a square. We're going to increase that and see how fast the area is changing. So we want to remember, for any rectangle, area is going to be length times width. But this is a square. So any rectangle, the area is length times width. Since this is a square, sides are equal, right? A square doesn't have a long side and a short side like any rectangle would. For this, we're going to have our area equals whatever the sides are times each other. They have equal lengths on each side. So the area is really going to be whatever the side length is squared. So that's our equation that relates these two things. The area is whatever the side length is squared, because when we do length times width, they're the same number for a rectangle. So if the length is 5, the width is 5, and our area is going to be 5 squared, which is 25. Once you have your equation, you can go ahead and take the derivative of it with respect to time. Everything's changing with respect to time, meters per second. So I'm going to take the derivative of 1a. It's going to be 1. And we just took the derivative of area with respect to time. Same thing with s squared. I'm going to take the derivative of it, bring down the power. The derivative is going to be 2s, but we just took the derivative of the side length with respect to time. The nice part about this compared to the dy dx problems is you don't have to think about, does it get that derivative at the end? It always does, because we're taking the derivative of two things with respect to time, and neither of them are time, unlike the other problems where you have the derivative of both x and y and you're doing it with just respect to x. So the y's got a dy dx, but the x's didn't get one of those. Here everything does. Now we want to figure out what we know. So we are going to be plugging into 1 dA dt equals 2s ds dt, and these numbers that we're given must be something. So we are going to have a for area, we're going to have s for side length, and then we're also going to have their corresponding derivatives, dA dt and ds dt. So the first thing we were given is the sides of a square increase at a rate of 3 meters per second. So that must be one of the derivatives, right? Area is going to be in meters squared. Side length is just in meters. How area is changing is going to be in meters squared per second. And how sides are changing are going to be in meters per second. Since we're talking about meters and second here. So this first piece we're given, this 3 meters per second, according to the units, can only be dSdt. Is 3 meters per second. We also know it's dSdt because it says the sides are increasing. It doesn't say the area is increasing by 25 meters squared per second. Otherwise, we'd put that in as dAdt. But this is the sides are changing by 3 meters per second. And since they're increasing, it's going to be a positive 3 meters per second. Note that if it was decreasing by 3 meters per second, we'd plug that in as a negative 3 meters per second. The other piece of information we are given is that the sides are 10 meters long. So it can't be a derivative. It's not going to be dA or ds dt because it's not given as a rate of change. It's just 3 meters. And so that must be sides, or in this case, 10 meters. Sides are going to be s equals 10 meters. And now we're solving for at what rate the area is changing. So we're missing dAdt, which is fine. We are given a rate and solving for a rate. So we're given how the sides are changing. We want to figure out how the area is changing. We're missing a variable here. We weren't given what the current area is. It doesn't look like we need it according to our derivative. There's no place to plug in a regular a anyway, so we don't technically have to find it. But I'll show you how to find it just in case you're ever missing a variable and you need it to plug into your equation. If you're missing a variable, you're not missing a derivative. That's normal. You're always solving for a derivative that you're missing. But if you're missing a variable, plug in to the original equation. So if I'm missing area, I can find that. Area is whatever the sides are squared. So the sides are currently 10. So side times side, we're going to have 10 times 10. Area is going to be 100 meters squared. When we square 10 meters times 10 meters, we get 100 meters squared. If we need it, but for this one, we don't technically need it. Because when we go to plug in and we're replacing numbers, well, we don't have dAdt, that's fine. That's what we're solving for. 1 times dAdt is just dAdt equals 2 times my current side length is 10 meters times dsdt is 3 meters per second. Getting bigger by 3 meters per second. So we're just going to multiply these together. 2 times 10 times 3, we're going to get 60, and we have meters times meters, so we're going to get meters squared per second. As sides increase by 3 meters per second, the area does what? Increases or decreases? We got a positive answer, so the area increases by 10 meters. 60 meters squared per second. If we got a negative answer, we would say decreases. As sides increase by 3 meters per second, the area also increases by 60 meters squared per second.